In this video, we're going to learn about random number generation in Python and if statements. Generating pseudo-random numbers is useful for statistics, working with probability, and modeling chance. These numbers are not truly random. They're random in the sense of the respective distributions that they come from and their statistical properties, but they're pseudo-random in the sense that a sequence of pseudo-random numbers can be reproduced. Python generates random numbers using the random and numpy.random modules. We'll only be talking about random today, but you should look at the functions in numpy.random as well. Functions in both of these modules generate random floats and integers from a variety of distributions. Beyond just generating random numbers, you can also do other random functions like shuffling lists and arrays in place. Seed can be used to reproduce pseudo-random numbers. After we learn how to generate random numbers, we'll look at if statements. Boolean logic statements are either true or false. Equals equals, not equals, greater than, less than, greater than or equal to, and less than or equal to are all common Boolean operators. If an if statement is true, the code after it is executed. If an if statement is false, the code after it is ignored. Else and else if statements are conditional on the if statements that come before them. And, or, in, and parentheses can all be used to add complexity to Boolean statements. So let's get started, and let's start by generating some random numbers. We have to import a module in order to generate random numbers in Python. We'll be looking at just the random module today, but you should also look at the numpy random functions as well. We'll also be generating graphs to look at the random number outputs that we'll be generating. So let's also import matplotlib and pyplot as plt. And also remember that you have to use the matplotlib inline function to make plots as well. So let's press Shift Enter and execute that. The first function we'll be looking at is called random. In order to look at this function, though, we have to type random before the random function, and we put two parentheses, and we press Shift Enter. And what we get is a random float between 0 and 1 that is inclusive of 0 and does not include 1. These random floats come from a uniform distribution, which means that all numbers between 0 and 1 are equally probable of being selected. And if we execute this cell over and over again using Shift Enter, we get a different random float each time. Random number generators are completely compatible with all the functions we've already learned about in Python. So let's use a for loop to visualize the outputs of this random function. So we're going to create an empty list to store the outputs of this function. We generate list again by using empty square brackets. And we create our for loop, and we say for a variable I in the range. And let's make a ridiculously large number of something like 1,000,000. And we always put a parenthesis, and then we are indented. And we're going to say for 1,000,000 times, we're going to generate a variable in, that is the output of this random number generator. And then we're going to our random list. We're going to append this value of n each time. And then we want to visualize our results. So we're going to say, call pyplot and look at a histogram, which is used to visualize distributions. And we are going to look at our random list, and there are 30 bins in our histogram that we're going to look at. So this for loop just executed 1,000,000 times, and then we look at our histogram, and you can see indeed that this is a uniform distribution that's including 0 but not including 1 of floats between 0 and 1. So the random function creates random floats between 0 and 1. If you don't want your random numbers between 0 and 1, you can specify whatever you want them to be. And there is another function called uniform, and it goes between between any two numbers that you want. Let's say 1 and 100. So this will include 1 but not include 100. So if we press Shift Enter, we're going to get a number of different random floats between 1 and 100. And again, we can keep on doing this. So again, let's create a for loop to visualize the outputs of uniform. We have chosen arbitrarily a beginning of 1 and an ending of 100. And we will execute this function a million times. But actually, for this function, let's start at 1 and go to a really high number, in this case, a billion. So a million times, we're going to select random numbers from a uniform distribution from 0 all the way up to a billion. You can see, indeed, this distribution is a uniform distribution. What if you wanted a different distribution, though? What if you didn't want you wanted random numbers, but not from a uniform distribution? Let's look at a normal distribution or a Gaussian distribution. Again, this from the random module, we're taking this function Gauss for Gaussian or a normal distribution, and we give it two different arguments. We can give it a mean and a sigma value or a standard deviation. So let's pick a mean of 42 and a standard deviation of 2. And again, let's use a for loop to look at the outputs of a million uses of this Gaussian function, again with a mean of 42 and a standard deviation of 2. So if we execute this, we can look at the output and we get this beautiful normal distribution. This is only 30 bins, but remember that we called this a million times. So the shape of this distribution should be very fine. So let's make our bins 300. And then you can see that we should have a much finer distribution. And again, you can see we have this very fine distribution now. So this is with the Gauss function where you give it a mean and a standard deviation. Our mean was at 42 and we had a standard deviation of 2. So you can look at other types of distributions than just uniform. And this is very useful for statistics. Beyond generating floats, you can also generate integers. So we can do this with the randint function for integer. And this function, unlike the uniform functions, is inclusive of the beginning and the end. So let's go from 0 to 6, and it will give us a random integer between 0 and 6. And we can keep on rolling the dice, and we'll always get 0, but we should get also 6 inclusive eventually from this function if we execute it enough. This is the problem with random distribution random number generators. You never know when you're going to get the number that you want. We're not getting 6 here. Let's keep on doing this. Eventually, we should get 6 inclusive. And I just want to show that because the other uniform distribution functions don't include the endpoint. There we go. We finally got a 6. So you can get 6 inclusive from the randint function. There's a lot of other random functions you can use that are not just random number generators. For example, you can shuffle a list. This is very useful for bootstrapping approaches and other randomization. So let's just create a list. We'll just call it my list. And then the random.shuffle function will in place shuffle your list. So if we call this function and then we print my list again, it should be in a shuffled order. And there we go. We had 0 through 5, but now we have 5, 4, 0, 2, 1, 3. And if we keep on executing this cell using Shift-Enter, we're going to get a different order each time. Again, this is very useful for bootstrapping and other randomization approaches where you need to shuffle a list in place. So that's a bit about how to generate random numbers. There's many different functions in Python, and especially in the NumPy module, there's many different types of distributions you can choose from. And so I really encourage you to look at all the ways you can generate random numbers in Python. So now that we've learned how to generate random numbers, let's use them to look at if statements. And let's begin with Boolean logic. Boolean logic is, these are statements that can only be true or false. And they're generally evaluated with numbers, although you can look at strings as well. And you can evaluate using equals, not equals, greater than, less than, and a lot of other different functions. So let's just create some numbers here. We're going to create A as 42, the answer to life, the universe, and everything. Another famous number, let's make it pi, 3.14159. And let's make C equal to 42 again. So we set these variables by pressing Shift-Enter. Now, Boolean operators, for example, you could say, are two things equal to each other? And you might think that you look at that by saying A equals B, except this is problematic. What's going to happen is we're going to set the value of A to B. So if we execute this function, it sets the variable A to the value of variable B, so that if we press A now, it's 3.14159, and that's, of course, what the value of B was. So all we accomplished with an equal sign was to reset the value of A, and that's not what we want. So let's reset our value of A again back to 42 by pressing Shift-Enter. And the way that we do a Boolean equals operation is we use two equals sign. And this is exactly to avoid the situation that you just saw where you reset the value of a variable. So if we say, does A equal B, that is a false statement when we use two equal signs. It is false that 42 equals pi. Does A equal C? And the answer to that is true. They are both 42. So let's just go through all the different ways that we can look at these operators. Remember, A and C are 42, B is pi. So is A greater than B? That is, of course, a true statement. Is A lesser than B? That is a false statement. Is A greater than C? That is a false statement because A is equal to C. But is A greater than or equal to C? That is a true statement. And is A lesser than or equal to C? And that is a true statement. So Boolean logic is either true or false. Those are the only two outputs. And this is very convenient for coding and for the understanding of computers. And so oftentimes we find ourselves trying to figure out how to do something that we want to do, but using Boolean logic. So now let's get to if statements. An if statement is very much like it sounds in natural language. Let's create three variables again, A, B, and C, except this time we're not going to know what they are ahead of time. A, B, and C are going to be random numbers that are generated between 0 and 100, random integers. And let's print what A, B, and C are. And then let's write our very first if statement. So in an if statement, you start with if, and then you make a Boolean logic statement. So let's say if A is greater than B. And then you put a colon, which is just like a for or a while loop. So we say if, and then we have a Boolean statement. This Boolean statement can be true or false. If it's true, we run the code after the if statement. If it's false, we just ignore the whole if statement. So if it's true, we run the code within it. Just like a for loop, the colon is important and the indent is important. So make sure that both of those things are there, a colon and an indent. And then we put code within our if statement. So if A is greater than B, if that's true, we will print A is greater than B. If this is false, the code will be completely ignored. So we should get nothing. So let's press Shift-Enter and see what happens. We get A is greater than B, and A is indeed greater than B. If we run this again, A is again greater than B, 89. Let's run it again. A keeps on being greater than B, and eventually A is not greater than B. So what is happening is if this Boolean logic statement is true, then we run the code. If this Boolean logic statement is false, we just completely ignore the code beneath it. So if we keep on running this again, here is an interesting example. A was actually equal to B. So it was not true that A was greater than B. We do not run the code. And again, A is greater than B, and then we run the code. So what happens if we actually run multiple if statements now? So let's put another if statement after this. Let's say if A is greater than C. If A is greater than C indent, then we print our some code, and A is greater than C, if that's true. So let's run this again. A is greater than B, true. A is greater than C, true. What happened is this was true, so it did the code. Then it went down to this second if statement, saw that it was true, and ran the code. This next time, this second one is true. So what happened is A is greater than B was not true. We had no print statement. And you can see that B is greater than A. So this statement is not true. A is not greater than B. We just ignore the code. We do not print this statement. But then we went to the second if statement, and A was greater than C, which is true. 58 is greater than 26, and then we print A is greater than C. So these are just two independent lines of code. If this is true, do that. If it's false, ignore it. Then we go to this one. If this one is true, do that. If it's false, just ignore it. So these are successive lines of if statements. Let's put all possible scenarios where something can be greater than the other. So B could be greater than A. B could be greater than C. And C could be greater than A. And also C could be greater than B. So no matter what, one or more of these statements has to be true. It's just impossible. And for each of these, we're going to put the respective if statement of what they are if it's true. So no matter what, something should be printed. A is greater than B, A is greater than C, B is greater than A, B is greater than C, C is greater than A, C is greater than B. So if we run this, there'll be multiple things, or at least one each time. So A is greater than B, A is greater than C, B is greater than C. We can run it again. A is greater than B, A is greater than C, B is greater than C. And we can keep on doing this. B is greater than A, C is greater than A, and C is greater than B. So we can keep on running that over and over again. But let's try an experiment here. Instead of having them all be at the same indent, let's indent them all one over. So now this one is the first if statement, and then we have all these other statements. So what's going to happen here? Unlike before, we would evaluate if statement. If it was true, do it. If it was true, do it. If it was true, do it. But in this case, with this first if statement, if it's true, then everything in this indent will be evaluated. But if this is false, nothing will be evaluated. So the idea is only if A is greater than B will the rest of this be evaluated. So we should either get A is greater than B with potentially other things, or we get absolutely nothing. So let's see how that works. See here we got absolutely nothing. And you can see, is A greater than B? No, it's not. 50 is not greater than 55. What happened is this first if statement was false. It was not evaluated. And so all the code that's indented after this if statement is just completely ignored. So let's run this again. A is not greater than B, so the rest of the code doesn't work. A is not greater than B again. Finally, A is greater than B. And then when A is greater than B, all the rest is evaluated. A is greater than B, C is greater than A, C is greater than B. So these indents matter. And it's the way it works is that if the statement is true, everything in the indent is evaluated. If it's not, nothing within that if statement is evaluated. It's a little disappointing when in fact A is less than B because you get no output, and you may be wondering, well, what's happening? Because you just don't know what's happening. So let's look at the else statement. The else statement always comes after an if statement. It has a colon as well. It has an indent, and you can put code in here as well. And we're going to put else A is not greater than B. And so else statements are used if this is true, then all this code runs, and then we ignore else. But if this is false, and if other things between this if statement and else statement are also false, as a last-ditch scenario, if nothing else is true, then by default we'll just do what the else statement says. So again, if this is true, we run this code, but we ignore else. But otherwise, else, if this is false, then we run the else statement. So let's run this a few more times. A is not greater than B. So this was false, and we went straight to the else statement. If we run again, again, A is not greater than B by 1. Finally, A is greater than B. And then we look at the other statements. A is greater than C, and B is greater than C as well. You could do it this way, where you have nested if statements. But this is a bit cumbersome because everything is dependent on this being true. There's no other scenarios besides either this being true and running the code or false running the else statement. Another possibility besides nested if statements is something called else if statements. And else if is abbreviated ELIF. And again, this sounds just like you say it. So if A is greater than B, then we do that. And if this were true, we ignore all this other stuff. But if this were false, then we're going to go here. So else, if this is false, else. If this is true, then do that. But again, if this was false, we go to the next else if statement. So an else if statement is kind of like a backup. If this is false, we're going to evaluate each of these. As soon as one of these is true, though, we exit this whole logical hierarchy. So let's say it was actually the case that B was greater than A. This would be false, and this could be false too, and this would be finally true. So we do what was here, and we had already ignored this, we'll ignore the rest of it as well. It might be that it's all the way down here that finally an else if statement is true and that you would do it. And again, you would ignore all this would be true, and you would not do else. If all of these things are false, only then would you do the else statement. So let's look at this. This says B is greater than A. So A was not greater than B. That's true. A was not greater than C. That is true. But B was greater than A, 21 versus 94. It was the case, for example, that C was greater than B. But we didn't evaluate it because this else if statement was true first. As soon as you hit a true else if statement, you exit this logical sequence here. And only if nothing is true do you get to the else. So let's run this a few more times. Let's look for one. A was great. In this case, A was greater than B. The very first thing was true. And we don't even go to the else ifs. B is greater than A. We already saw that. Let's look for a C is greater than something, maybe. Or maybe we're not going to get it. But A is greater than C. On the second time, that was true. And as soon as that was true, we exited. In this case, A was not greater than B. I hope you understand now how if, else if, and else statements work. You generally put something that is of importance of whether it's true or false. And if that's not the case, then you can evaluate a number of else if statements. And finally, if none of this is true, you can finally look at an else statement. You can also, for these Boolean logic statements, use and or as well. So let's look if A is greater than B and A is greater than, if A is greater than C. And if this is true, then A is the greatest because it's greater than both B and C. And again, like we just learned, we can put an else statement if we want, and the else statement would be A is not the greatest. So let's evaluate that. So using an and statement, both of these things have to be true to say A is the greatest. A is greater than B, A is greater than C. If either of those is not true, A is not the greatest. So A is not greater than B, and A is not greater than C. In this case, A is the greatest again. Let's try to get where A is in the middle. So A is greater than B in this case, but A is not greater than C. So one of these was false. And so with this and statement, if one of them is false, then this is not true. So A is not the greatest. You could also do an or statement. So if A is greater than B or A is greater than C, we could say, for example, A is not the least because A is greater than B or C. So A is not the least in this case. It's greater than both B and C. A is not the least in this case. It's greater than B, but it is not greater than C. So even though this is false, this is true. So because it's an or statement, A is not the least because it was true that A was greater than B, even though A was not greater than C. And you can do really complex things with and or in parentheses. So let's look at if A is greater than B and A is greater than C. And that will be one statement to evaluate. Or let's say, is B greater than A and B is greater than C? And we're going to say if either of these two compound and statements are true, then C is not the greatest. So if A is greater than B and A is greater than C, or if B is greater than A and B is greater than C, C is not the greatest. So C is not the greatest in this case. And here C is between A and B, and it's not the greatest. So A is not greater than B. A is greater than C. So this was false. But B was greater than A, and B was greater than C. So C is not the greatest. So just know that you can make very complex statements that can allow you to do very sophisticated things, even though this is just Boolean logic of true and false, that all these conditions can allow you to do very sophisticated things. And let's just end by doing a very sophisticated random number generation and if statement evaluation. So we learned about the Fibonacci sequence, and this includes 0, 1, 1, 2, 3, 5, 8, 13, and 21. So we'll have a list, Fibonacci. And we're going to create random numbers, and we're going to put the numbers we generate into these empty lists. So let's create a list called my Fibonacci, and we'll create one called my even, and we'll create one called my odd. And then we can say for I in range, and let's look at 100 numbers. And again, we're going to create a random number and keep it as a variable as in, and let's generate random integers between 0 and 30. And then we say if, another way you can do a Boolean statement is if n is in the list Fibonacci. So as we're generating random integers, if they are found in this list, then we do this if statement. So if they're in this list, then we will append them to Fibonacci, and we'll append the number in. If this statement is false, we will proceed to an else if it was false. And let's say that if it's an even number, then we will append it to the even list. So this is a modulus. It divides the number by 2. And if the fractional component after dividing by 2, that's what a modulus is, if the fractional component is equal to 0, then we know that that number must be even. And so if it's even, then we append the number to my even list. Else, and you can use else statements in a very sophisticated way, that if everything else is false, it must be true, for example, that the number must be odd. So without even evaluating a statement, we could assume that the numbers are odd, and we can check this, of course, as we run this function. And so there we go. If it's in the Fibonacci sequence, it will go to the Fibonacci list. If it's even, it goes to even. Else, it has to be odd. Note that the way this works, that the even numbers or odd numbers that are Fibonacci will not go to the even or odd list. They'll first go to the Fibonacci list. So we'll evaluate the output of this. We'll say Fibonacci numbers are, and then we print the list my Fibonacci. And then we can print even numbers are, and we can say my even. And then we can print odd numbers are, and we can say my odds, or my odd. Fibonacci's are my Fibonacci, even numbers are my even, and this needs to be print. Okay, so, we had an extra S there. And so if we evaluate it, you can see that the Fibonacci numbers, if it's a Fibonacci number, if n is in the list Fibonacci, we put it in my Fibonacci list. And so you can see these are all Fibonacci's. Else if the modulus of 2 is equal to 0, then it's an even number. And so you can see these are all even numbers. But notice that some of the Fibonacci numbers, like 2 and 8, are only found in the Fibonacci list, not in the even list, because they first went to the Fibonacci list and they're no longer considered to be appended into the even list. If these two statements are false, Fibonacci and even, we're going to assume that the numbers are odd. And you can see that these are all odd numbers. So if we keep on executing the cell over and over again, you can see that we're getting different results. And so let's execute it one more time, except that what we're going to do, remember that these are not truly random numbers. These are pseudo-random numbers. They're, if you give the generators a number, they will reproducibly create the same sequence of pseudo-random numbers over and over again. These numbers are truly random for statistical and other purposes, but they're not random in the sense that they can be reproduced and generated again. So if we do a random seed of 42 before we execute this code, we get a new set of numbers. But if we keep on executing this cell, because we're always starting with a random seed, we can reproduce the same exact sequence of pseudo-random numbers. And in that way, these numbers are not truly random, but they can be reproduced. So there we go. In today's lesson, we learned about pseudo-random numbers and how to generate them, that they're useful for statistics, probability, and modeling chance. Random number generation comes from the random and numpy.random modules. Function in both these modules generate random floats and integers from a variety of distributions. We learned how to shuffle lists and arrays. We just saw that seed can be used to reproduce a sequence of pseudo-random numbers. So that's all for this video. Thank you for watching.